Okay, so today we're going to be looking at a problem that comes up quite frequently, actually, which is when we're looking for the closest orthonormal matrix to a given matrix. So we're often maybe given a particular data set, and we're looking for the nearest version of that data set which is orthonormal, whose columns are unit norm and are mutually orthogonal. Okay, so how are we going to find that? So first, let's formulate the problem. So we're going to be looking for the nearest orthonormal matrix. Okay, so what does that mean? So what are we given? So given a square matrix X, find an orthonormal Q that minimizing, and we need a notion of nearness here, so we're going to use the element-wise distance, so the also in the Frobenius norm. So minimizing x minus q. So this is the problem that we have. Okay, and we're going to be able to solve this problem very readily using Lagrange multipliers. We're going to be looking for, the arg min over q of 1/2 of x minus q, such that q transpose is the identity. So this thing is our orth condition, and this is our kind of nearness. So we want to minimize this distance such over this set of orthonormal matrices. Okay, so if we want to solve this problem with Lagrange multipliers, we're going to need a Lagrangian. So let's write out our Lagrangian. Plus the trace, and we're going to pack all of there's going to be one Lagrange multiplier for every single element of the matrix Q. Okay, so now let's write this second term, this first term in its trace form as well. So this is just going to be 1/2 trace of x minus q times x minus q transpose. So plus trace of ... So that's just this. Okay, great. So now we want the gradient of this Lagrangian with respect to q. And the way we're going to find that is by looking at the differential of this Lagrangian to minor perturbations in Q. So let's just see what happens. So dl is going to be equal to trace minus dq x minus qt minus trace lambda t dq qt minus trace lambda t q d q t. Okay, just a couple of things to notice here. So let me just switch to the laser pointer. So here what happened was there was two terms here, the x minus q and the x minus q transpose, but because of the symmetry there, we can just pretend like there's one of them. So just deal with this one, put the differential here, and take care of the fact there's two of them by getting rid of the 1/2 and replacing it with a 1. So there's actually two symmetric things going on here when we took the differential of this first term. And the differential of the second term is just the standard thing. So it's the differential contribution from Q, which is this, and the differential contribution from Q transpose, which is here. Okay, great. so now we want to, to get the gradient. The gradient satisfies dl is going to equal to the trace of the gradient with respect to q of this transpose times dq. So I think the simplest way to be able to read this out from our differential is to just move things around so that these dq's are sitting as they are in the rightmost position of each of these expressions. So, for example, we want to move this guy over here, this guy over here, maybe, and this dq transpose, we want to convert it into a dq. So we're just going to do that using the simple properties of the trace, which are its circular property, its invariance to transposition as well. Okay, so what we're going to do is, at the top, we're going to move. The very first thing we're going to do is we're going to move this guy to that side. So, and all we need to do is applying the circular property. So it's minus x minus q transpose dq. So that's the contribution from that term. For the second term, we're just going to apply the circular property. So just shift this guy over, move the dq to the right. So let's do that. Minus trace q transpose lambda transpose dq. Now, for this final term over here, we're going to first apply transpose to make the dq transpose a dq. So let's do that first. So it's going to be minus trace dq q transpose lambda. And then we're going to, this particular one is we're going to apply the circular property twice. So we're going to say this is equal to minus trace of q lambda dq. Okay, and so now now we can just rearrange. We can now combine all of our terms here. So there's going to be minus trace of x minus qt dq minus trace qt lambda t dq. Finally, minus trace qt lambda dq. Okay, so now we've got everything in the form that we wanted. So we just collect these the contributions to the gradient from each one of these terms, and we end up with the gradient with respect to q of L is going to equal to minus x minus q, because remember we have to take the transpose of the things that are multiplying dq, minus q minus, just like that. Okay, and we set this equal to 0, and we get is equal to okay, so we've set this expression to 0, so x minus q moves to the left-hand side, and these guys stay exactly where they are. We just collected terms. Okay, so now we recall our condition that at the optimum, qt equals I. Okay, so now when we do that, when we have that condition, we write multiply by qt, and so then this becomes xqt minus I is equal to minus just like that. Okay, so now, or which then becomes xqt is equal to I minus. Now at this point, it turns out we won't actually have to figure out what these Lagrange multipliers are. The main thing we need to conclude is that xqt is symmetric, right? Because this is symmetric, sum of symmetric terms stays symmetric. Okay, so to go further, we're going to now apply SVD to x. So x is equal to u s v transpose. So this is just SVD. So xqt is going to equal to u s v t qt. And we've just said it must equal xqt transpose, which is equal to qxt, which is equal to qv s u transpose. Okay, and we can just see by comparing this with this that qv must equal u, which then implies that q is equal to u v transpose. Okay, so what this means is that the nearest orthonormal matrix to x equals u s v transpose has the same left and right singular vectors, so that's u and v, but has unit singular values. So if x equals u s v t goes to q equals u v transpose. So that's just one way of solving this problem, showing how we can do it with Lagrange multipliers. There are other ways, and one final point is that this is a special case of what's called the orthogonal Procrustes problem, where in that situation we've got our target matrix x, and then we've got a second matrix y, and we're looking for a rotation that can rotate y into x. So where we minimize, so in that case it's going to be such that qt equals I. So our problem corresponds to y being the identity. Great, so hopefully that was useful. Just showed you how you can use Lagrange multipliers to solve this problem of finding the nearest orthonormal matrix that comes up all the time. Let me know what you think in the comments. Thank you.